Welcome back, everyone, to the fifth part of the lecture. We're gonna talk about the results of this project, and I hope you have understood so far, like the main idea of this project, which was to create a novel antenna design for energy harvesting purposes. Okay. Before we get into the results, we need to explain something very briefly, which is the voltage standing wave ratio, and it's just the measure of impedance matching it of loads to the characteristics impedance of a transmission line or waveguide. Meaning, when we talk about the 50 ohm impedance, needs to be matched between the feeding line, the circuit, and your antenna needs to match 50 ohm. So this voltage standing wave ratio gives you the best, not the best, sorry, it gives you a result of how close or how well matched is your system. Okay. So now let's get into the results. As I said before, the antenna was excited with 1 volt at the port, and its S11 parameters, radiation pattern and electrical field, were calculated for frequencies between 0.86 gigahertz, 0.84 gigahertz, 1 gigahertz, 1.6 gigahertz, 2.4 gigahertz, 2.8 gigahertz, and 3.2 gigahertz. Okay. The figure on the left, it shows the distribution of the electric field and the radiation pattern in the antenna. It displays the hotspots. It means where the antenna is capturing all this energy, or it's either taking it or reflecting it. And this is the 3D version of the electric field, normal to it. It's displaying the hotspots on 1/4 of the wavelength, corresponding to the port in the antenna. We can see here is 0.84 gigahertz, and we can see that most of the power is being radiated outwards. As you can see, 0.84 is minus 3.9 dB, which means most of the power getting into the being collected by the antenna is actually going out of the antenna. So you are not harvesting any power, and any value that is above 2.5 for the voltage standing wave ratio, it means that your system is poorly matched. So there is no much matching for this specific frequency. Okay. So this table depicts the result from the simulation, the S11 parameters, the impedance at the port at this specific frequency, and the lump port power, how much power it's getting obtained from this. So at 0.84 you get 5.98 milliwatts and minus 3.9 dB, which is very bad. At 1 gigahertz you get 7 milliwatts, 6.6, which is starting to get better, and 2.73 for the voltage standing wave ratio. But still, if you can see here, we said that the impedance should theoretically match 50 ohms, and if you're close to 50 ohm and a bit above to 50 ohms, it's still good. It can still work. Okay, but below 50 ohms, it usually doesn't work, as you can see. So when we get to 1.6, it becomes clear that things start to improve from there. So the antenna becomes more responsive at such frequency. So as it can be seen, at 1.6 gigahertz, the antenna will radiate the best with a S11 of minus 24.5.6 dB. So this can also be observed from the radiation pattern. Let's move forward. So the radiation pattern, or the electric field of the electric field at 1.6 gigahertz, you can see that most of this energy is being soaked, is being taken by the antenna and stored it. So you can see from here, this is hotspots. It means that most of this energy is being stored in the antenna. Then if you go to 2.4 gigahertz, it also gives you a good response. You can see this red spots. And 1.6, you have 1.12 voltage standing wave ratio, and which means anything that is very close to 1 1.5, 1.1, it means that the system is matching with your antenna is matching with the feed line, okay, with the circuit or the feed line in this case. And you can see it from the lump port impedance. You have 46.4 ohms. Don't worry about this imaginary cases. You only want the real case, the real argument of the value, because you're only looking at the real part. But we all know that impedances have real and imaginary values, okay? Then 2.4 gigahertz, your system is collecting a lot of power as well, 9.74 milliwatts. This looks small, but for a system that is capturing energy from the air, technically from nothing, these are good results for this type of geometry. At 2.4 gigahertz you get minus 15, which is very good. 2.8 gigahertz you get minus 12. 3.2 gigahertz you get minus 14. So it is clear to us that at 1.6 gigahertz the system behaves better, and the antenna behaves better at 1.6 gigahertz, which is also in agreement with I don't know if you remember, but for energy harvesting frequencies from the previous study that I mentioned, that between 900 GSM to 1.8 GSM, 1800 GSM, you can harvest a lot of energy, which is in agreement with that paper. Okay. Okay. So I already discussed this at 0.84 gigahertz. You are reflecting most of the power, and no power is being stored in your device. And at 1.6 gigahertz, almost around 3.84% of the power is being reflected, and this is good because you're getting most of it into the antenna. 96%, 97% of the power is being stored in your antenna. And then we go to the radiation pattern, and this is a 3D version, and this is how your antenna behaves. Okay. So this antenna, an antenna, as we mentioned earlier, is a device that captures or sends information or sends energy. In this case, at 0.84 gigahertz, as you can see, most of the power is being reflected back, and the antenna is behaving uniformly. You can see it from here. The antenna is behaving uniformly. So there is nothing getting in the antenna, and everything is getting out of it, most of it. So you can expect these results because the antenna it's forming a ball type of shape, and that means that it's uniform. Then we go to 1.6 gigahertz, the radiation pattern, and then you can see interesting stuff. It starts to behave in omnidirectional waves, which means that it receives and it's receiving signals from all directions. Okay, so you can see it from here. At 1.6 gigahertz, you're getting power. You're receiving power from all directions, from this phase, from the other phase. If you go back, you can see that it's getting power from these places. At 2.4 gigahertz, it also behaves omnidirectional, but it's capturing most of its energy from the top. You can see here top and bottom. That's why there is they are red here on the top, but a bit blue on the bottom. And if you see it from the other side, they're a bit red also. But for 1.6 gigahertz, you can see most of the energy it's being taken into the antenna. So your antenna is being excited from all the places, and it's very interesting because it's receiving signals from the top, from the bottom, and this is small depression here, you can call it, I guess. It just means this part, the ground plane. Okay, it's mostly the ground plane, and it means energy is being reflected back, and nothing is getting into the antenna basically. There is, and this is the interesting result. Then if you go to the radiation pattern, also, I'm sorry, I was gonna show you something. Okay, I'm gonna show it. The radiation pattern. Then in 2D you can see the polar Smith charts, which is how you can also, it tells the same story. It tells the same story of these plots and as this plot, but now using polar charts. Okay, so it can be seen at 0.84 gigahertz that it is exhibiting a distribution from 0 degrees. You can see here from 0 degrees, 210 to 270 degrees here, and it's roughly uniform. It's a uniform distribution, as we talk about it here. It's a uniform distribution. Nothing is getting into the antenna. Everything is being reflected back. Okay. Now, when we go to 1.6, 2.4 gigahertz, things become more interesting because the distribution of 15, you go for 50 degrees, 60 degrees, and 120 and 300 degrees. As you can see here, this blue line, it's 1.6, 120, 300 degrees, 15 degrees, and it's telling you the whole story, that it's behaving in an omnidirectional radiation. It has an omnidirectional radiation pattern, meaning that it is receiving power from all its sides. Okay, we already saw it here. It is receiving power from all the faces, and you expect these results from the Smith charts. And at 2.4 gigahertz, it also have a directionality. It behaves similarly, but with less power as than 1.6 gigahertz. Okay, and now some of the other important parts, the global voltage sine wave ratio. So we plot the system behavior from 0.84 gigahertz to 3 gigahertz. So we can see that this also agrees with our results. At 1.6 gigahertz here, you get the best voltage sine wave ratio for your system, meaning that at that frequency, and 1.6 gigahertz, there are many phones that work, and many applications that work at that frequency. So you can really obtain a lot of benefits from it. So like from the phone calls, from messaging, and you can harvest this frequency. So at this point, you get 1.6 gigahertz, and you get almost 1 of voltage sine wave ratio, meaning that your system is matched with 50 ohm between the feed line and the antenna. And the S11 parameters, that it describes how the system behaves and the power. We can also see that at 1.6, sorry, there is almost minus 25 dB, which is way smaller than minus 10 dB, and your system is behaving not efficiently. Okay, it's doing a good job. And this concludes my explanation. But before that, I'm going to show you the results in console. So we go to console, we go to study. If you want to run your program, you need to go to study and you need to give it frequency. So from here we go 0.84 to 3.2 gigahertz, and you need to teach the system how is it going to solve this problem. So this problem is solved by iteration. So we iterate from 0.84 to 3.2 gigahertz, and the system is going to run through all these frequencies and give you the result. So these are the S11 parameters. Now the electric field, so the radiation pattern, we can see from here the radiation pattern of also in the far field normal. can see for 2.4, 2.8 also. You can we can plot it for 2.8. It becomes a little bit more distorted at these frequencies. It doesn't behave as good as at 1.6, and at 1 and 3.2 you see there is a bit, it doesn't behave as good as 1.6. But at 1.6, and this also shows you that the antenna behaves as a monopole. So this is a very cool thing, and it also shows you that it's a monopole antenna. Okay. Now the surface electric field, you can see at 3.2 power is getting reflected, and not much is getting into the antenna. Let's go to 0.8. 84. Sorry. Okay. 0.84. Sorry, because I have this. Okay, so 2.4. Sorry, there is a problem with this. Okay, so at 0.84. Okay, now it's working. 0.84. Most of the power is being reflected back. You can only see power through the feed line because you're feeding the antenna from this point, so there must be a lot of power, but most of the power is being reflected back. Okay. You go to the impedance map. We all know how this map works and graph from electromagnetics. It's an impedance graph. It's a Smith chart. So here you can basically write or plot how well matches your system. So if we go and we take all of these values, you can really match it, and we need to remember that, okay, how this works. So here is the non-real scale, and then you have the real scale, and then you normalize this data, and it gets plotted like this. Okay. Okay, this is the voltage standing wave ratio. You can just plot it by using this command on console, and the global. You can also plot it using this command. Okay. So now, as for the future work, in the future, the authors, me and my project supervisor, Professor Jihad, were planning to continue in the study and improve the design by adding other types of dielectrics. Dielectrics, they can be metamaterials or different types of dielectrics that can improve or enhance the performance of the device. The authors, also anyone who is listening to this and is interested in this and who wants to get into the workarounds of RF technology, energy harvesting technology, you can send me an email to me or Professor Jihad, and I can provide you with the codes and with the project report and the simulation files, and you can try them yourself. Okay, these are some reference from these are the reference from the papers that I used that were more insightful to me while doing this research. Thank you very much.